All right, so in chapter 12, we're going to be taking a closer look at some of the functional groups that contain atoms other than carbons and hydrogens. And here we're going to be focusing on our alcohols, thiols, ethers, aldehydes, as well as ketones. And you got a preview of these functional groups at the end of chapter 11 when we had gone through and listed essentially all of the functional groups that we're going to be encountering in this class. Now we're going to take a look at some of the specific properties of these functional groups. So just to remind ourselves what they kind of look like. So alcohols are going to contain a functional group that looks like this. There's an OH attached to something, right? And remember this bond here that seems like it's not connected to anything, that just means it's connected to something else, right? Typically it's going to be connected to that OH connected to a carbon, and that carbon could be part of a longer carbon chain as well. So the way that we'd represent that generically, we can say ROH, right? Remember we used this R notation before. R just means any carbon containing group. Right, so for example, if that's just a CH3, we end up with a molecule known as methanol. Phenol, we saw this as well as a derivative of benzene before, so this is a special case where you have your benzene connected to an OH group, right? So that itself is known as phenol or phenol, depending on how you want to pronounce it. Thiols contain sulfur in them, and specifically they're going to contain SH connected to an R group, right? So just like with the alcohols, right, we can write a thiol as R SH, where R represents any carbon containing group, right? So you'll probably notice here that the thiol is similar to the alcohol, the ROH, right? They have a similar makeup and they look kind of similar. Instead of an O, there's an S in the thiol. And if you look where oxygen and sulfur are on the periodic table, that should make a little bit more sense to you, right? They're right above each other, right? Oxygen is right above sulfur, sulfur is right below oxygen. They're in the same group. And then finally here in this subsection, your ethers are going to contain an oxygen that's between two R groups. All right, so there's an oxygen between two carbons, in other words. All right, and the simplest ether that you can have is going to have an oxygen between two methyl groups. All right, and we saw these before briefly. Now we're going to take a look at some examples of these and how we name some of them. So just to sort of show you a couple more examples, we talked about methanol, CH3OH. That is our line angle formula. Phenol, benzene with an OH attached. Here's a thiol. There's the SH group that's attached to a carbon containing group now. That's an ethyl group on one side. And here's our ether, the oxygen in the middle that's surrounded by two carbons on either side. All right, so we're going to focus in first of all on our alcohols, and we're going to name them according to the IUPAC or the systematic way. And the way that we're going to name these alcohols is similar to the way that we've named all our molecules so far. We want to get the longest carbon chain that has the OH group, the alcohol group, attached to it. All right, so just a little bit of a clarification. The OH, right, we look for that tells us something is an alcohol, but the OH itself is actually called a hydroxyl group, right? And the presence of that hydroxyl group tells you that it's an alcohol. So we want to get the longest continuous carbon chain that has the OH group attached to it. And what we're going to do is we're going to name that longest carbon chain as a typical alkane. So we're going to drop the ending of the corresponding alkane name, which is the E, and we're going to replace it with OL. Right, so that OL in the name tells you that it is an alcohol. Right, so the ending here tells you what functional group it belongs to. All right, so for example, if we had a molecule that looked like this, right, our longest continuous carbon chain here is 2, right? So a 2-carbon alkane would be ethane. What we're going to do is we're going to drop that ending, which is the E, and replace it with OL. So this becomes then ethanol. All right, you'll also notice that there are certain alcohols that have common names associated with them. We're not going to focus too much on the common names, but I just wanted you to be aware of that. You will see those names actually more frequently than you may think. All right, so ethanol is also known as ethyl alcohol. Right, that's the active ingredient in your alcoholic beverages. Methanol is also known as methyl alcohol. Right, but we're gonna prefer, when we start naming things, all right, we're gonna use the systematic way, the IUPAC way, to name our alcohols and everything else that comes after it. When the carbon chain gets a little bit longer, then we have to explicitly state where the OH group, where the hydroxyl group is attached. So for longer carbon chains, we're going to have to number the chain. And again, the numbering here is dictated by the lowest number possible for the OH group or the hydroxyl group. All right, so if we have this molecule down here, all right, so it says give the IUPAC name for the following compound. First thing we need to do is to decide what the longest continuous carbon chain is that has the OH group attached to it. All right, so we start from the left, 1, 2, 3, 4, 5, 6. If I start from the top, I still get 1, 2, 3, 4, 5, 6. If I start from the right side, I get 1, 2, 3, 4, 5, 6. Or if I go up here, 6 is the longest. All right, so we can just draw a box around that longest continuous carbon chain, and we're going to prefer to number it, or we're going to want to number it from the right side, right? Because we want to give the OH group, the hydroxyl group, the lowest number possible. Right, we're going to circle our substituent groups. So this then, right, would mean that the hydroxyl here is on carbon number 2. So the OH. And then we also have a methyl here on carbon number 5. So that's a 5 methyl. All right, so then we can put our name together. We have a 6-carbon alcohol. So this is going to be hexane, would be a normal 6-carbon alkane. We're going to drop that E ending, replace it with an OL. And then we need to say now where the OH is attached. It's on carbon 2. So it's 2-hexanol. And then we also need to include any other substituent groups, right? So our 5-methyl goes in front. So 5-methyl 2-hexanol. Again here, the hex tells us we have a 6-carbon chain. The OL tells us there's an OH group present. The 2 tells us where that OH group is located. All right, so it's a similar naming strategy that we've used for our organic compounds so far. All right, if you take a look at a slightly different example, right here you don't see a chain, you actually see a ring, right? And what you should notice now is that ring is attached to OH, so that means that it's a phenol. And by naming it as a phenol, this carbon here has to be carbon 1. All right, and then you can see that there's a bromine attached to it. We want to number it to give now the lowest number possible to that bromine. So we'd want to go counterclockwise. So 1, 2, 3. So that would be a 3 bromo. And then phenol would be the last name. Right, and that's systematically how we would name our alcohols so far. Just to give you an idea of a couple alcohols that you may be aware of, right? So we mentioned ethanol. This has been around for a very, very long time. It's found in alcoholic beverages. Right, it is the active ingredient. Most commonly, it's made by the fermentation of different types of sugars. Right, and typically substances or organisms like yeasts, for instance, can carry out that process, right? So glucose, which is a sugar, which is a type of sugar, can be fermented to produce ethanol, and then you get CO2 as one of the other byproducts. Ethanol can also be made in the lab by a slightly different way, by the hydration of ethene under high temperatures. All right, so ethene can react with H2O. Remember, when you do this hydration reaction, you think of the water as an HOH. The H goes to one carbon and the OH goes to the other carbon of the double bond, right? So we end up with our ethanol in this case. Other types of alcohols that you'll see, this one here is called glycerol. Right, glycerol is also known as glycerin, and this is very, very, very common. It's found in a lot of things. It's found in things like skin softeners, skin lotions, cosmetics, shaving creams, soaps, lip balm, all sorts of things. It's a very, very, very common type of alcohol. It is actually known as a trihydroxy alcohol, meaning there are 3 OH groups in it. Right, and those OH groups are in carbons 1, 2, and 3. Right, so if you were to name this, right, it would be a 3-carbon chain would be propane. When you have multiple OHs or hydroxyl groups, we're going to use the prefix di, tri, tetra, and so on. So we have 3 of these, so this will be a tri, and then we have the ending -ol. Right, so the -ol tells us it's an alcohol. The tri here tells us that we have 3 of the alcohols, and the prop here tells us that there are 3 carbons. And then we also need to say where those 3 hydroxyl groups are located. They're on carbons 1, 2, and 3. Right, so that's the systematic name for it. It's commonly known as glycerol or glycerin. Another very common alcohol is called ethylene glycol. And ethylene glycol is also known, or is also found in antifreeze, and obviously it has its use as in preventing, the freezing of the liquid in your radiator, for instance. But it's also used in the production of other things. All right, so if we had to name this one, right, our longest carbon chain here is 2. Right, and here we don't have just one OH, we have 2, so it would be ethane diol, and then the 2 OHs are in carbons 1 and 2, so we'd say 1, 2 ethane diol. That's the IUPAC name for ethylene glycol. Ethylene glycol is the common name for this thing. Another alcohol that you may be, or a phenol that you may be aware of, is something called bisphenol A, or BPA. And as you probably know, that's found in containers, usually the clear plastic ones, baby bottles, drinking bottles, etc. And BPA, under certain conditions can actually leach from the bottles and get into your liquid, right? So you want to be extremely careful with that. So this is the chemical or the structural formula for bisphenol A. You can see that there are two phenol functional groups in this, and they're both attached to a carbon in the middle. All right, this is the common name for this. We won't worry about the systematic way to name that. That tends to be a little bit more challenging. But we could name it if we wanted to. Certain types of phenols are also found in as uses in other things. So for example, if you look at some of these flavoring and essential oils for different plants that are responsible for odors and flavors, we can actually see phenol being a very big part of these structures, right? So for instance, vanillin up here at the top has that phenol part of it. And vanillin obviously is what you find in vanilla, right? And that's the agent or the chemical in it that is responsible for the odor and the flavor of that plant. Thiols, as we saw before, contain sulfur. Specifically, it is one of two functional groups that contain sulfur, the other one being the disulfide. Thiols contain a thiol functional group, which is an SH. Thiols typically have a very, very, very strong and repulsive odor or stench, I would say, associated with them. All right, and they're found in things that have really bad smell. So for instance, cheese, onions, garlic, for instance, they contain all different types of thiols in them. The spray from a skunk also has a thiol in it, right? And there's your thiol functional group. That's the SH there that's attached to that carbon chain. Thiols are also used, not only are they repulsive, but we can actually take advantage of that really bad smell. They're actually added to natural gas, because natural gas doesn't have a smell, so it's odorless. So we add these thiols to it so that if there is a leak, for instance, we know, right? Our nose is going to tell us that there's a gas leak. So what you're smelling when you smell a gas, leaking out when you turn your Bunsen burner on, for instance, that's not the gas that's burning, right? That's not methane or ethane. That's actually the thiol that's put in there to make you aware that the gas is flowing. All right, so the naming of the thiols is going to be a little bit more straightforward. We're just going to add the word thiol to the end of the alkane name of the longest carbon chain, and then we're going to say where that thiol group is located by numbering the carbon chain closer to that end of where the thiol is. All right, so for instance, we'll kind of draw some comparisons here. Right, a one carbon alcohol is called methanol. Right, so we saw that methane became methanol, the alkane became the alcohol. In the case of the thiol, right, we're just going to add the word thiol to the end. So a one carbon thiol is methane thiol. A two carbon thiol is ethane thiol. When you start getting to higher and higher number of carbons, so longer carbon chains, right, you need to include where the SH, the thiol group, is attached. Right, and again, just for clarification, the presence of the SH tells you that that thing is a thiol. The SH itself is itself referred to as a sulf hydryl group. Right, just like the OH was called a hydroxyl, the SH is called a sulf hydryl group. So in the case of this one here, right, you can see that the longest continuous carbon chain that has the sulf hydryl attached is 4. Right, so that would be a butane, and there's an SH, so that makes it a thiol. And we'd want to number this chain from the left side to give us the lowest number possible for that sulf hydryl, which is on carbon number 2. Ethers, we saw, contain an oxygen that is sandwiched between 2 carbon groups, and those 2 carbon groups can be anything, right? As long as they contain carbons in them that's sandwiched in oxygen, then that is an ether. So generally, we can say an ether is ROR, where R is any carbon containing group. It can be a single carbon or it can be 50 carbons long. It doesn't really matter. So ethers kind of resemble the shape of water, which we know is bent, right? So if you remember, water looks like this, and there are 2 lone pairs on the O. So if we were to draw an ether properly, it would actually mimic that shape, right? With the 2 lone pairs on the oxygen. The way that we name the ether is we are going to name them according to the common naming system. All right, so we'll only use the common names of the ether, and the way that we're going to name these is by naming each alkyl or aromatic group attached to the oxygen, and we're going to write those in alphabetical order, and then we're going to end the name with just the word ether at the end. All right, so for instance, if we had something like this, all right, first thing you have to do is to realize that's an ether. There's an oxygen here between 2 R groups, right? This R group on the left, a carbon containing group, that's a 1 carbon group, that's a methyl. And then the one on the right side has 1, 2, 3, 4 carbon group, that's called a butyl. Right, so all we're doing is we're going to insert these names in front of the ending for the compound, which is ether, and we put them in alphabetically. Right, so B comes before M, so this just ends up being butyl, methyl, ether, all one word. All right, similarly, if we had something like this, all right, there's our oxygen between 2 carbons, so that's a 2 carbon group on the left, a 2 carbon group on the right. This is an ethyl on the left, ethyl on the left. This is an ethyl 2 carbon group on the right. Right, so this ends up being diethyl, and then it's an ether, so we stick the word ether at the end. Diethyl, ether, and it's that simple for naming ethers. All right, ethers have historically been used as anesthetics to knock people out when surgery, for instance, had to be done. But one of the problems with those ethers originally, for instance, like diethyl or dimethyl ether, is the fact that they were very, very, very volatile and flammable, and they tended to induce nausea, right? So people would vomit, for instance, when they woke up. So those ethers are still around and they're still used, but they have since, some of the hydrogens on them have since been replaced with other atoms like halogens in order to reduce the volatility and the flammability, right? So a very common one that's used is something called furane or isoflurane, where several of these H's have been replaced by either fluorines or chlorines, right? So you'll still notice here that they're still ethers, right? The O between two carbons would make it an ether, and that's the case for all of these. Right? They're still derivatives of ether, and they still have that use as anesthetics. All right, so let's just finish up this first section here with drawing the structures. All right, so I want to draw first of all 3-pentanol. All right, so again, when you draw these, you want to start with the last name first. So pentanol means 5 carbons, and the 3 here tells us the OH is attached to carbon number 3. All right, so I'm going to draw my 5 carbons, my root name or my ending 1, 2, 3, 4, 5. And then my OH is attached to carbon 3. So 1, 2, 3, 4, 5. And we're going to stick my OH on carbon 3. That's 3-pentanol. Ethanol. All right, eth here tells us it's a 2-carbon alcohol. So 1, 2. And then a bond to OH. I could have drawn it this way with the OH at the front. All right, that's the exact same thing. And then diethyl ether. All right, so ether means there's an oxygen between 2 carbons. We have 2 ethyl groups, so two carbon groups on either side. So on the left side here, there's 1, 2 carbons. On the right side, there's 1, 2 carbons. All right, so that's your diethyl ether.